Já estamos transmitindo ao vivo aqui, por favor. Passo aqui a. Pode. Sou Fred, pode ficar à vontade, já está transmitindo ao vivo.
Okay, thank you, Mr. Adilton. Obrigado, Adilton. I'll speak in English because our guest speaks English, and we'll have an international speaker today. It's my great pleasure to have here with us Professor Tilo. I would like to say just a few words before I hand to Gabriel, who spent 2 years with Tilo in his lab in the MGH. So, first of all, thank you very much, Adilton and Fernando, who's not here, for arranging this event. We've been planning this event since 2019, I guess. It was scheduled for the first time for the first semester of 2020, but we had just a small delay, and now we're here. I'm very happy. I'm sure we'll have a great event. So thank you very much for arranging the things, for arranging the channel, the technical things for this event to happen. So, and before handing to Gabriel, I'd like to say tell a bit the story of how I met Tilo. I've been for a visit, to visit his lab in 2005, I guess, 2006 maybe. Yeah, the end of 2005 and the beginning of 2006. And my contact was Professor Marcos Francisco Vidal Melo, former professor here at the university in our program, biomedical engineering program of Federal University of Rio de Janeiro. And it was a very top tier lab. They produced very high quality research, and I went there to get to know, get acquainted to the methods, to the group, to get to know the group. And Professor Tilo was put in charge of communications with me. And I was a bit insecure. I was a bit intimidated, I must admit, because it's just this very strong group. And I asked Professor Till for directions to take me there, to get me to the lab. And I received. I'm really sorry. I didn't keep the message he sent me back. It was really detailed, very accurately detailed set of instructions on how to come from Providence, where I was staying, all the way to the door of the lab, to the very door of the laboratory, where he was waiting for me, and everything went really perfect for in the first trial. I was exactly at the door of the lab. I knocked the door, and there he was, Professor Tiro. So this little story is not just to say that Professor Tilo is a gentleman. He's very kind. He's very he gives much importance about the relationship between people. He's very gentle, and he's very accurate in his descriptions. And I was really happy. And from then on, I felt much more secure about being there in the lab, because I knew there was someone who was taking very good care of things there. And also, not just because of that, I'd like to say that when we are in person, when we are physically in some places, in the places, in the meetings, um, there are many other things that happen just like this. Many other things that happens that uh, makes the bounds between us. It's very important. I think this occasion is very deeply it remains in my memory. I'm telling this story right now because it's really strong, held in my memory, and I think it's important. I hope that we can be together in a very near future, Professor Tilo. I hope we can arrange for your visit, long-awaited visit here in Brazil. So thank you very much for being here. I'll hand to Gabriel for the introductions. Gabriel has been there for 2 years, and he's co-organizing this event with me. So thank you, Gabriel.
Oh, thank you, Freddy, for the first introduction. I will say just a few words about Chilo and his career to get here. So Chilo is a German from Dresden, and he made his undergrad there and master's and PhD in biomedical engineering. And then he went to the US, Boston, to make a postdoc and stayed there since. And that it was now is an associate professor on the Harvard Medical School and the Massachusetts General Hospital, and made a great work with this lab that he arrived and was doing this different thing and doing positron emission tomography of the lungs and all this multifunctional imaging that can give us different perspective of this in vivo perspective of this organ. And Chilo will talk about his work, and I will hand it to him. And was a very nice person to meet and stay with this time. Thank you.
Thank you very much for the kind introduction. I appreciate it, and I feel the same. So it's a mutual feeling, the connection, and I hope that we can expand it beyond exchanging scientific talks and some ideas, that we get a more substantial collaboration going between MGH and groups in Brazil. I'm very fond of it, and I'm looking forward to it, to expand on that part.
Okay. You're listening, Fred? It's okay?
Sorry, I just lost a little bit of Tilo's, the last part of the last sentence of Tilo. So I think we can hand to Tilo to good.
Okay, good. Now, just to say that for us, as biomedical engineer, it's a big pleasure to support this webinar for all SBAB community and use our platform to keep this material with a real-time transmission for our community and keep record for new or the future of students. So for us, Professor Chile, it's a big pleasure in name of a biomedical engineering society, Brazilian society. Thank you so much. Have a good webinar. Now I put Professor in the main screen. Just
Tilo, can you share your presentation now?
Hold on. No, sorry.
Sorry, I'll stop my camera. Maybe Professor Tilo could
yes.
have his presentation now.
So is everything okay? I don't have a feedback here. Hello?
okay, Professor Tilo, you are listening. You can continue, please.
Yes, okay, yeah. I just wanted to check because I didn't have any feedback, so I was not sure if everything is okay or not.
It's perfect. It's okay. You can continue. Thank you.
Yeah, let me know if anything happens because I may have limited feedback of noticing what's going on your side. Yeah.
Okay.
So thank you very much again for having me, for the invitation. I really appreciate it. To make a bridge between MGH Boston and the Brazilian groups in biomedical engineering. So by training, I'm a biomedical engineer coming from Dresden, Germany. But I think I have turned a little bit more towards science. And I guess during the talk, it may become clear how this may have happened. So I will talk about the pulmonary imaging and modeling at the edge of studying lung diseases. And it's a bit of my personal story too that is behind all this work, but it's also a selection that I made today to primarily for a biomedical engineering audience rather than respiratory or pulmonary audience, which is more clinical and the focus may be slightly different otherwise. So I have no relevant relationships to disclose for full transparency. So respiratory research has a very long and rich history. So I put together here a few slides to emphasize it. So on the very left, you see there's a drawing from Leonardo da Vinci around 1500s, where he detailed, so there was clearly an understanding of the structure of the airways, that the airways were branching inside the lungs and the blood vessels were branching as well. In the middle, you see a cast that was made by filling in the airways and the vessels, and you can appreciate the arterial vessels, so pulmonary arteries in red, pulmonary veins in blue, and yellow is the airspace, so the airways and the alveoli towards the end. I think that's the most detailed cast that I have seen. And you overlaid, you have a little bit of a schematic of the branching airways all the way to the terminal alveolar units. And on the right side, you have maybe the first, the oldest I could find. They call it mercurial breath holder and breathing machine. So where a patient would expire into that machine and would allow the researcher or physician to measure how much volume the patient, the subject, exhales. And by doing so, there is an opening then to understand, can this measurement be linked to disease, right? Does the person of different size with a different disease be able to exhale more or less volume, and can this be used as an indicator, as evidence that the patient may require certain treatments? I think it's very nice. It's sort of a mechanical engineering involved in that device too, which today has all changed. It's more electronic. So what I emphasize here already from the historical perspective is there is, which is highly emphasized in respiratory research. I don't have that much a feeling for other fields, but in respiratory research, we talk about it again and again. There's structure on one hand and function on the other hand. So the two are interlinked. It's sort of a dialectic relationship, we could say. The one cannot really exist without the other, right? So there are the airways, for example, right? The airways are an anatomical structure, but then they fulfill a function. And the functional aspect is more measured by this mercurial air holder, and the anatomical is more described here on the left side by assessments, by microscopy, and measuring anatomical sizes, etc. So the first, or the oldest modeling of airway resistance I'm aware of comes from Rohrer in Zurich, Switzerland, 1915, published in 1915. So he was the first to use tubes to simulate, to model the resistance to airflow that airways would have. And he was asking questions of how different resistance may affect the distribution of airflow in a branching pattern like the airway tree. So this is the first kind of model, more of a mechanical background of model, rather than in contrast to mathematical modeling that we may use today, but very efficient. And he set it sort of in motion, we could say. So to go a little bit more into detail on the modeling and different aspects and how we might describe it, I put on the left side a schematic of the branching network of airways. So that follows a little bit more the idea of a symmetrically branching network that Edward Weibel had used for his analysis. And he came to the conclusion that there are about 17 to 18 generations of branching airways until we come to the terminal airways where we see the first alveoli, which is called the respiratory zone. And then there are a couple of further generations of branching within the alveolar units. So, but the high structure, spatial structure of the lung is not really causing how should I say, is not visible in the external signal. So we can, if all the airways are similar in a symmetrically branching tree, we can collapse it to a single airway resistance. And the elasticity of the lung could be reduced to a single compliance. So then we have a model that has now one resistance, one compliance, and maybe would assign to the chest wall and the diaphragm a so-called chest wall compliance. Then we come, if you use symbols from electrical engineering, which I find very convenient, we get the airway resistance, a more schematic assessment or visualization of that model. And then if the lung is now not healthy, if the lung becomes changes because of disease, other things that may happen, or there's a deviation from a normal healthy condition in the lung, then we may need different functional units. So the functional units on the right, you see, I thought that there could be parallel compartments. So these would be functional compartments. They may be associated with anatomical structures, but not necessarily. So if there would be two regions, anatomical regions, that have the same functional properties, they may collapse into one functional compartment. So this is very important from the basics of modeling that I wanted to emphasize in this context of biomedical engineering. I think there is an understanding that reality is the given infinite complexity that may exist in the real system. But based on the purpose or an aim that we have to describe some part of reality, we draw a boundary, and we may call this what's inside the boundary the system that we try to describe. Now, we make a reduction from the complexity of that system, what we try to describe, and describe only certain elements of it. And I think so the understanding is there that there is reality on one side, and the model, incomplete model, as a reduction on the other side. But what is often overlooked, and I think it's very important to keep that in mind, is that there's a purpose. So if I develop a model for one purpose, it may not be suitable for another purpose. And we will see how this plays out in respiratory physiology. I can give some examples. So if we take the more complex model on the right side, so where I thought, okay, maybe we can have several functional compartments. Now, I explored at that point the possibility. I was wondering, if we have different model structures, often we have the assessment that we can compare different models. We can simply ask the question, which model describes these signals, the reality best, the measurements best. And that model should have an advantage over the auto model, can better explain reality. Now, if you want to do it, I have sketched here a couple of different configurations I could think of. I would be interesting to learn if I can differentiate these different functional assessment structures inside the lung, because they could potentially be relevant. There's, for example, one ongoing debate or discussion in the field more related to asthma and COPD, if the disease may be more in the central airways or more in the peripheral airways. And there's some arguments and hope that it may be possible with measurements at the mouth, with pulmonary function tests, to differentiate if the disease in the central or peripheral airways, which could affect what type of inhaler would be needed to reach those airways. So we can take these different configurations and make a model. So there is a very well-established, rich literature on model identification and modeling, so particularly linear time invariant systems. So conceptually, we would say that we have an input signal U, an output signal Y. There is noise superimposed to the output signal. And now we try to estimate filter A and B such that the parameters of the filter minimize the error between the two signals. So when we do that, when we formalize that, we come to a transfer function, which is GRS, so the RS for respiratory system, the transfer function of the whole respiratory system. So on the top right, you see the equation with a Laplace transformation with 6 parameters, 3 persistence and 3 compliances, the structure that I had shown before. And we can reduce it to a transfer function that is more associated with the ARX model on the left. We get 3 B parameters and 2 A parameters. Unfortunately, the 2 A parameters are linearly interdependent, so that we have actually only 4 independent parameters. So if you have only 4 independent parameters, you cannot estimate 6 unknown variables that are in the original model. So that means beyond 4 parameters, there is no unique solution for additional parameters. And it turns out that the 6 different configurations I showed that I was interested in potentially in differentiating, separating, understanding central versus peripheral airways, etc., all have the same structure of the transfer function. So how the B's and A's are associated with resistant compliances, that may be different, but the transfer function is the same. So that means that all the models are essentially equally well suited to describe the relationship that we can measure at the mouth. So here with airway pressure at the at the airway opening at the mouth and the flow that's going in and out. So I just want to emphasize again, so that I'm not talking here into the empty space. If you have any questions, please feel free to jump in. I mean, I find it more satisfying when we get into a conversation about the topics. I notice where you may have questions, where I should go into more details, or where I could go faster. So please don't hesitate. Here is a model that we had developed in collaboration with Hamilton Medical in Abanadout, Switzerland. So we were interested in developing a model for the relation mechanics that I had shown before that describes the relationship between pressure and flow for a condition where a patient may be mechanically ventilated in an intensive care unit. But we didn't want to limit it, and here comes where we go beyond, where we need a different scope of the model. We didn't want to limit it to the ventilation mechanics, so only concerned with the pressure and flow. In fact, relative pressure to barometric pressure. We wanted to include gas exchange, because if in a patient there are different functional units, they may be ventilated differently, but how does it affect the gas exchange? How does it affect how the oxygen goes into the capillaries, reaches the arterial blood? And then in the periphery, we have respiration, so the oxygen goes into the tissue. CO2 is coming out of the tissue, is returning to the lung, and should be eliminated through the lung by ventilation. So all these processes interact with each other, and there are changes in the blood. So we developed this system that allows up to 10 compartments in the lung. Parallel compartments, functional compartments that we can assign that would be different. For example, how well they are ventilated, or what is the relationship between ventilation and perfusion. All this affects the gas exchange, as we see in general. So this model includes, beyond what we had originally, which was purely ventilation mechanics. That includes ventilation mechanics, the transport of gases through the airways into the alveolar space, where there is an anatomical dead space through the airways, where there is no gas exchange, and the fresh air coming in has to overcome the dead space before it reaches the alveoli and can diffuse into the oxygen, diffuse into the capillaries, and the CO2 is coming back and will be eliminated. The gas exchange in the alveolar unit, which is diffusion, and then on the blood side, we have to deal with a bit of the chemistry of how partial pressures of the gases translate into oxygenation parameters that are, for example, oxygen saturation. So how many red blood cells are actually oxygenated? What fraction of red blood cells is oxygenated? So this was very successful and gave us some idea. So we put it into a computational model so that can be used for educational purposes. So we are not able to estimate all the parameters absolutely accurately that one could attempt to run a simulation for a patient and find a better setting before going to the patient and applying it. But the model was intended to prepare this sort of development that controllers could potentially be developed that automatically adjust the ventilator within certain constraints. So on the top, this schematic, this screenshot shows the flow signal, and constant inspiratory flow, followed by a pause and passive expiration. So then several breathing cycles here, a little more than 2 breathing cycles. In the middle, there's the volume, when the constant flow is going in, volume is going out of the lung, and then there's passive expiration. On the bottom is the pressure. So we see the jump in the pressure, for example, on the left side. That is from the resistance. Then comes the slope. Here's a linear slope here. That's the compliance of the lung that is expanding. When the flow stops, we have a sharp drop, idealized to a plateau. When the flow is zero, that's now the alveolar pressure. And then the expiratory valve of the ventilator opens, and we have a passive expiration. So what is now limited to what we can measure at the airway opening, and we can never look inside the lung if different regions of the lung may be affected differently. And maybe if they contribute much less than 10% to the total signal that comes in and out of the airway, maybe it's even difficult to distinguish that signal from the noise in our measurements that we have anyway. So it's now relatively well established that I think that computed tomography is used in the ICU for respiratory purposes, for example, but also for assessment of people with emphysema, where part of the lung tissue gets destroyed. So here we have on the left the schematic of a CT. So there's an X-ray tube that is rotating around the body. On the opposite side, we have detectors. So we get attenuation images, and we get many attenuation images in many different angles, from which we can reconstruct a three-dimensional field of the attenuation, which I put one slice on the right side, but in fact, from CT images that we take from animals and studies or patients, subjects, we get in the order of several hundred CT slices with relative thin, that are relative thin. And the noise is amazingly not that bad, so that allows us to analyze a lot of anatomical structures. CT gives us insight into anatomical features, anatomical structures. You can see in the center 2 airways and some blood vessels. Unfortunately, I don't have a pointer here that I could point you to it. So if we take the stack of CT slices, we can run software. Others have developed software, for example, Vida, but also a couple of other companies for an automated segmentation, or Slicer has some algorithms as well, so that we can, the algorithm would follow the airways and make a cast, or a virtual cast of the airways as much as it can recognize the airway clearly. So there is, from the CT, because of still limited resolution, at maximum, if the patient takes a very deep breath, we get 6 to 7 generations of the airway. From the 18, or the total is about 24 if we go to the very periphery of the alveoli. So we have a limited view, but nevertheless, we can make some measurements on the central airways, which can be very helpful, or we can make projections. Also, you see that the lung was segmented, right? So today, there are algorithms based on neural networks using some methods from AI that try to improve that segmentation process. Yeah. So CT is, I said, basically a structural assessment. All what CT can give us is density. Density in the lung is associated with structural measures. It can hint at functional differences, but it's not itself, I would argue, a functional aspect. So is there any way that we could use CT for functional assessments? And I wanted to talk about this seminal work from Professor Gabriel, where he took an inspiratory CT and an expiratory CT and used an elastic registration algorithm. You can think of it like you have one image, an image A and an image B, and the algorithm that's slightly deformed, right? Because one is at the end of inspiration, the lung is larger, and the other one is at the end of expiration, the lung is smaller. So we have anatomical features, airway vessels that change. So the algorithm gets the task to find a solution of mapping the end inspiratory image to the end expiratory. And if that solution is good, or accurate, we should say, or sufficiently accurate, then the change gives us an idea of how much regional change, lung expansion we have. And that is a measure of strain. So why are we concerned about it? In mechanical ventilation, particularly when not in the healthy lung. I mean, the healthy lung is typically not a big deal, and it's relatively homogeneous. But when the lung is injured, the distributions become heterogeneous, and there can be high local concentrations of high strain, while other tissues have experienced much lower strain. So we are concerned that the high strain, so when you think of it, the tissue is highly stretched, that it causes injury, causes further damage, and potentially the prospect for the patient to recover from the need of mechanical ventilation is lower, and there's a risk of ventilator-induced lung injury, as we call it. So he compared in the study in an animal model, supine position and prone position. And when you look at the color scale that is on the right side, you can appreciate that in the supine position, you have much higher strain values than in the prone position. And that is related to how the lung mechanics work in the different body positions, right? So gravitation acts on the lung. It's not the same. Part of it is that there is a vascular tree and an airway tree inside the lung. So he demonstrated that the strain heterogeneity, not the strain itself, but the heterogeneity, is significantly different between the prone and the supine group. And you see that in the prone group, we don't see substantial changes, but in the supine group, the strain heterogeneity, or another measure is the 95 percentile over the mean, increases substantially in supine position over time. And to further exploit how that is spatially actually distributed, where the high strain and the low strains occur, we made these 3D renderings. So on the right side, you see the distribution of the strain, and you see the color scale. So the medium values are sort of taken out by applying full transparency. So we look at the low strain and the high strain areas. So we are more concerned about the high strain, but the low strain may be an indicator that the distribution of the ventilation is not well. And by having low expansion in one part of the lung, if the tidal volume, so the total volume coming into the lung, is the same, of course the expansion in another part of the lung has to be higher. So looking at the low part is somewhat an indicator of what may happen in other parts of the lung as an increase of expansion. So here we had talked about the structural aspects. Now, when I came to the lab had already started using positron emission tomography. So Professor Venegas, Jose Venegas in Boston, a senior principal investigator, had established a PET measurement. And so here's the schematic of a current scanner on the left, labeled here as A. And then one scanner that is currently, there's only one prototype exists, which is a full body PET scanner. And the difference between these two scanners couldn't be bigger than. I find it astonishing, the first images and videos that came from the total body scanner to compare to what we have today. If that becomes widely available, the limiting factor at the moment is cost because of the expansion of the detector blocks that are blue on the outside. But if it becomes widely available, that will be a quantum change in terms of imaging quality and what we can do in terms of imaging time. The sensitivity of the total body scanner is simply much, much higher than the current scanners have. And that would allow us to do to use lower activity of an isotope that we need for the imaging. I need to get to this. And shorter scan times, a lot of advantages also with dynamic scans. So there can be static scans, that is important. CTs are typically static images of the lung. In PET, we also take snapshots, but often we take a whole series of snapshots to get a dynamic PET scan. On the right, there's a schematic of the positron decay. So we use isotopes that release a positron. And that is a remarkable story in itself because the positron that's coming out of the decay of the isotope is an antimatter particle. So this particle cannot exist in our world. It gets scattered in the tissue slightly until it's slow enough and meets an electron, and then the two are annihilated into two gamma rays, two 511 kiloelectron volt gamma rays, photons. So that means there is a fundamental aspect in this simple sounding explanation that matter, the electron and the positron, disappears, gets converted into energy. And in fact, that the positron is coming out of the decay. The positron cannot exist in the atom because it would annihilate with other particles, with the electron particularly, right? So the positron must be generated, come into existence, in a material existence as a particle in our world when the isotope, so the atom decays, and it is then annihilated once it meets an electron, and the two are converted into energy again. I find it very remarkable. So here is an example of the dynamic PET imaging we are doing in a method we have developed. José Venegas particularly has pioneered the method as a bolus injection. So with that we get, you see the schematic, how the activity is injected at the very beginning at time 0, is reaching the lung, and there is a breath hold as indicated on the top, and there is a high diffusion pressure because the solubility of nitrogen 13 is very low, so it diffuses into the airspace. So at the end of the breath hold there is a plateau, and the plateau, the distribution that you see on the right side, is proportional distribution of perfusion. Now the subject or animal then resumes breathing, so the ventilation. That means the activity is now removed by ventilation. And that means we get, with the first part of the dynamic PET image, a perfusion image, and from the washout by ventilation, we get a ventilation image, regional ventilation. And I hope you can appreciate the residual activity at the end of the washout in that case. This is relatively normal. I want to first go into this before we go into disease configuration. So what can we do with the washout? What we had noticed that the regional washout follows different kinetics. And here's where the modeling comes back in. So you can see that I put a schematic here that with the 4 models we are using. One behavior we observe is regional single exponential washout. The other one, airway may be occluded, so the tracer is delivered by perfusion, but there is virtually no washout, so there is activity remains constant. Then there is a single exponential and gas trapping combined, or we have double exponential tracer kinetics. So that means with the kinetics, although we have PET has a lower spatial resolution compared to CT, we have functional resolution beyond the spatial resolution of the PET scanner. So we analyze the kinetics of all the individual voxels. We apply a selection method that's called Ike's information criterion, selecting for the best model fit, and take the parameter of the model that fits best into a global distribution that of ventilation and perfusion that is highly relevant. So that's one of the cornerstones of gas exchange, how gases are exchanged in general, but particularly oxygen coming uptake through the lung and CO2 elimination through the lung. And we validated it in an animal model that was highly heterogeneous, that the oxygen partial pressure, the arterial oxygen partial pressure estimated from our imaging study correlated highly with the actually measured arterial oxygen partial pressure in these cases. So what we can now do, we can have a fusion of the PET image and the CT image that allows us to bring the functional and anatomical aspects together. And that is not something minor. That's pretty important because often we can make sort of segmentations for the lung. For example, we have a better outlining of the lung. We know where the activity should be. We can identify, exclude airways or large vessels. We can check what the density of tissue is relative to the functional signal that we get from PET imaging. Many other aspects that are relevant in that context. So, as one example, I wanted to talk about bronchoconstriction in asthma. So, during asthma attack, as stimulus reaches the airway, the smooth muscle of the airway narrows the airway lumen, and the resistance is going up. Breathing becomes very difficult. But the aspect of asthma is that the constriction and the increase in resistance is reversible. So here is an animation of tracer retention in a subject where we had simulated an asthma attack. Is that a question here? Yes. Yeah, okay, I'll come to this. Where the asthma attack leads to airway narrowing. And during that simulated asthma attack, we inject nitrogen-13. We get a perfusion image and we get the washout. So this is the tracer retention. So that's at the end of the washout, what I mentioned earlier, showing that there is obviously high airway resistance in some parts of the lung, but not in others. So why is it so clustered? Why is it so concentrated rather than widespread? Why are not all the airways of the lung constricting? So here's a question about CT and PET have a resolution of almost 6 compartments. Yes, so we get regional resolution. We get basically thousands of parameters. I think in PET we may have so in the order of magnitude of about 30,000 voxels that we get. That gives us more of a distribution that it is related to global measures, but it has a different sensitivity. So that's important to understand. So the measures of ventilation and lung function tests, they rely on measuring the flow and the pressure. And once the washout from a compartment like we see here, the ventilation defect, the airway is mostly or totally occluded. These compartments would not show up in the ventilation mechanics anymore. What we may notice, though, is that the compliance is changing because only a part of the lung is still ventilated and the subject could exhale it. So this is one of the parameters, so-called FEV1, that is used in function test. That's simple, very limited, but very robust and frequently used in the clinic for that purpose. So why is that? Why do we have this clustering? We were wondering when we got these images. So could it be that something happens in the airways when they constrict, that they are not constricting homogeneously, but there is an interaction among the airways that leads to this clustering of severe constriction, while other areas are less constricted? So we built a model. We took the Anafi-Wilson model, which was built on the Live-Hook model, and built it into an airway tree with 12 generations using the geometry of the airways from the 4th to the 16th generation. And the important part is the airway has the smooth muscle, then if it is activated, pulling inwards, but the parenchyma is a counterforce, pulling outwards. And the airflow coming through the airway feeds the parenchyma surrounding the airway. So that if airflow comes through the airway, the parenchyma will tether the airway and support its opening. Yeah. So the counteracting force to the constriction. But if the constriction succeeds, it will eventually shut down the airflow coming through and the parenchyma forces will go down. So that means here is a potential for a feedback mechanism that can go either way. So the question is now, after we build this model, what is happening when we run it? So here's a schematic on the left of the 12 generations airway tree. The color is associated with airway diameter. So white is full normalized size, and then the airways would become smaller. They go into yellow, red, and black eventually. On the right side is the ventilation. So each ending of the airway tree corresponds to a little square where the ventilation is. Right now it's homogeneous and all airways are fully dilated. Now we stimulate the airway tree and I let the simulation run. So you see how the airways are constricting. Initially, it happens very homogeneously, but then suddenly there is sort of the constriction continues more on the left side here than on the right side. And you see that on the right side, the airways were so yellow, less constricted compared to the left side. So I rerun it. And you see how the configuration is changing over time. So why does it happen? So there's a feedback, and the mechanism can be explained in a simple example. So if we just consider a single bifurcation, and we look first at the airway that is. So the two are initially equal in the flow distribution, but now by a little perturbation, one airway becomes less airflow. Because it gets less flow, there is less tethering. With less tethering, the smooth muscle can constrict more. That increases the resistance for the decreasing the flow coming in and decreasing the tethering. So there's a positive feedback and the airway would constrict more and more. So these would be the airways that are now on the left side and where the ventilation may completely shut down. So you see these black squares there. The other pathway, now since we assume that for the ventilation it has to be maintained, the tidal volume is the same, so ventilation is redistributed. That means the other airway is actually receiving more flow. That means the tethering forces are going up and dilating this airway. The resistance is going down, so there is more and more ventilation shifting from one branch to the other. One is constricting severely and the other one is slightly dilating. So when we plot this over time with the normalized airways, you see initially there's a homogeneous constriction, and suddenly there is a symmetry breaking, as it's called in complex systems, that some of the airways start to dilate and others continue to constrict, but there's not only one symmetry breaking because of the interactions I just explained. There are several critical points, so to speak. Why does it matter? So in complex systems, or when we call about systems that exhibit phase separation, so where suddenly there's a change, there's a transition from one state and another, we have we may have an energy well where so in this simplified one-dimensional energy landscape here, when the airways initially constricted homogeneously, we were in that energy well. If we would reduce the stimulus of the smooth muscle, it would simply go back, nothing happens. But once we reach the tipping point, now suddenly the system changes into a different state. We get the differentiation, and from that point, it does not so easily return as it would if it was inside the original well. This concept of tipping points is essential or key to complex systems and emergent behavior. So we call it emergent behavior because initially there was no evidence for the symmetry breaking that happens at some point because of interactions among the elements of the system. The same happens when you watch murmuration of starlings or birds flying in a flock. So it's not that there is a master rule for the flock, but rather that the individual bird follows some rules relative to its neighbors, and that is building the flock. And that may be because a predator is close by to the birds stay together, but otherwise they can disperse when you change the conditions. So this was very successful combining imaging and modeling. Our seminar paper here in Nature, and we could demonstrate additionally that, for example, when we change the tidal volume, it would also affect the ventilation defects, the size of these areas where ventilation goes down. And in another paper, we demonstrated there are at least 8, 9 other physiological observations that seemed contradictory with linear approximations, linear models, but can be fully explained with this model of bronchoconstriction in an airway tree. So interestingly, in asthma, bronchoconstriction is the key aspect how it starts. But it turns out when we do our perfusion imaging, we notice very early that actually perfusion is reduced eventually. So that seemed logical because there's this concept in respiratory physiology about hypoxic vasoconstriction. So if the airway constricts, there would not be a sufficient Sauerstoff to avoid that low oxygenation reaches the alveoli. The smooth muscle on the vessels would constrict and reduce the blood flow to these regions, and they're preventing hypoxia, arterial hypoxia. So that made sense, but then we tried to prove it that is caused by hypoxic vasoconstriction. We did a study where we had the subjects with a simulated asthma attack and then breathing air or 80% oxygen, assuming that the 80% oxygen would relax the hypoxic vasoconstriction. You see on the top right that there is the specific ventilation. So that's the ventilation divided by the volume. That's so size independent. Was similar for room air, for air, and for 80% oxygen. In areas that we would call with low specific ventilation, which are the ventilation defects, and areas with high ventilation, which are the areas outside of the ventilation defects. So you see the change that occurs in the ventilation between baseline and bronchoconstriction. But there was no difference in the any specific ventilation between air and 80% oxygen, which is important, that the oxygen did not alter the ventilation side. Now the question is, what happens to perfusion? Here you see that the perfusion was reduced, but when we that's what we tried to prove, but it was not fully restored by the 80% oxygen, which was surprising. And we did, based on the very detailed information that we had with the ratio of ventilation and perfusion in each voxel, we could make a calculation of if that what the oxygen partial pressure in that voxel is. And there are sort of characteristics published that would establish at what level of oxygen partial pressure we would expect hypoxic vasoconstriction. And it turns out that the oxygen pressure should have been high enough to release the hypoxic vasoconstriction, but it was not restored in the areas to the full extent that we expected. So this is evidence that there must be another mechanism. We don't know exactly what it is, that mechanism that causes the reduction in perfusion independent of hypoxic vasoconstriction, but there are a couple of possibilities. One is that when the airway constricts, it may actually deform and change the hydraulic diameter resistance of the vessels, so blood vessels running along the airway, and that this could cause a change in resistance. But this is a hypothesis or speculation at this point, no proof yet. So I want to share a few more things, but I could go faster if that is needed. Should I speed up a little bit, Gabriel?
It's okay. We can continue. It's good.
Yeah, okay, good.
Yeah.
have a few more details that are exciting that I would like to share. So we have talked about asthma, the ventilation and perfusion, and the nitrogen 13, which is a tracer for us, a PET tracer that allows us to focus on the delivery, which is the perfusion part, and the elimination, which is the ventilation part. Now, in PET, there are many different tracers, and the real trick or the beauty of PET is that if a certain molecule can be labeled with an isotope, then we can watch where this molecule is going. So we are wondering in asthma. So if you get an asthma attack, asthma patients get an inhaler with bronchodilator. So does the bronchodilator reach the areas with a ventilation defect? Or could, if we were to use helium oxygen, could that make an entry for the aerosol to reach it? So we made the setup where we had a nebulizer, as you see on top, where we used a saline solution that was labeled with ammonia. The ammonia molecule was labeled with isotope nitrogen 13. So then if this gets nebulized and the subject inhales it, we can watch where the aerosol would go. Presumably, it would have the same distribution that an inhaler that the patient would use has. And we get an idea where how effective inhalers are, where the particles are deposited, and maybe if inhalers need a redesign. So here's an excellent visualization of a study where Elliot Greenblatt was lead PhD student at that time. And you see that the position is in red, so he put it on red. And in blue, at the bottom, you see where the ventilation defect is. So I think you can appreciate that when inhaled aerosol went to the ventilated areas, which means it would dilate the areas further and improve the ventilation outside of the ventilation defect, but would not lead to a recovery of the ventilation defect itself. Which I think is the separation between the blue and the red here is how should I say, a visualization of a thing where otherwise we can talk about it conceptually. We can say, oh, when the airways are constricted and the aerosol would not reach it. But here's the clear visual evidence of how this is happening. This is a different visualization of the same study. And you can appreciate that here he overlaid the PET data and additional information from the segmentation of the airway tree. So the airway tree is coming again from CT, the anatomical information, and we overlay the deposition, which is more of a functional information of the aerosol. And you can see how the aerosol has certain hotspots. So airways that are presumably very narrow and lead to hitting the droplets, hitting the wall, and therefore the aerosol would not reach or go deeper into the lung. Is sort of caught up like a trap for the aerosol, and we get hotspots. So you can appreciate the uneven distribution or concentration of aerosol on the airways, particularly on certain bifurcations. And here's an animation of one data set. Again, mixing the airway tree reconstructed from CT data, anatomical information, and the functional information, the activity of the aerosol. You can see there is one pipe in the center going down, is the esophagus. So some of the aerosol was deposited in the mouth, and the subject swallowed it and is going down the esophagus. We hadn't expected it, but it makes perfect sense. And you can appreciate the hotspots on certain airway bifurcations, and then the grayish areas in the periphery where a small amount of the tracer has reached deeper airways. In another study that I wanted to highlight here, we ask if perfusion may be changed in pulmonary arterial hypertension. So we had subjects that have hypertension during exercise, pulmonary arterial hypertension, and controls. And the point I want to make is that here we used a heterogeneity parameter. The trick in the data analysis, and that is not maybe the difference between engineering and being a bit of a scientist. The engineer applies, I think, certain principles to build something, construct something, but the scientist also has to be a bit more open-minded in the sense of exploration rather than applying and building things. But I think the two come very well together if you go in that direction, that you work more in exploratory basic research studies. The point here is that we want to demonstrate, we have the expectation that if we give the subjects oxygen and inhaled NO, that the perfusion would change somewhat substantially, and maybe by the change of perfusion would allow us to discriminate between exercise PAH and controls. It turns out that for the exercise PAH, that the heterogeneity was an essential part, not the perfusion per se, but the heterogeneity. And you can see that the red squares here are systematically on top, particularly in the range, so at 50-70, that's where we have the highest separation of the other two groups. So we have a discrimination actually for that set of subjects. If it holds true in a larger study, it needs to be tested, but it's a very promising result, I would say. And we can also show that when we look at the panel B, 50 to 7 millimeter range. So that's a length scale analysis. The way it works is we take the perfusion images, we start filtering them. And by filtering them, we eliminate heterogeneity. So applying a filter of 30 millimeter, for example, eliminates part of the heterogeneity. So then we can filter with 50 millimeters. The difference between the two is the length scale that was eliminated between these two filter steps. And that's the kind of spatial variation in the heterogeneity that we can characterize in that way. It's a bit like a spectrum, you can think of it. And interesting, so here we see that the heterogeneity appears to be constant, but I will show you now an animation of how the perfusion distribution looked like during air and oxygen with inhaled NO, how they changed. So this is the image. The mean perfusion was eliminated. So we look at blue is very low perfusion and orange, so the mean perfusion is fully transparent, that we can appreciate the change in low and high. The orange is very high, extremely high. The blue is very low. And you see that the low perfusion areas are substantially changing between oxygen and inhaled NO. Yet the heterogeneity in terms of the length scale analysis is remarkably constant. So it is the exploratory part where one has to have an open mind in terms of which parameter may capture and characterize a certain disease, a group of subjects or patients that we try to discriminate from others, potentially for diagnostic purposes or just to understand the disease, what these parameters might be. And it's always involves a little bit of intuition and guessing, partially based on prior experience. So here's a question: is there a common modeling strategy for different PEP traces, or it should be modeled from the first principle of the function observed? First principle is excellent, good starting point, as long as it works, because some of the tracer distributions following biological principles, and that is not so where modeling of the biological processes comes in. So there are still preservation of mass, so to speak, or of quantity, but the model parameters need to be estimated, the parameters of these processes. So there are common strategies for, or let's say, established strategies for certain tracers, but different tracers having different biodistributions may require different models. So I have talked about the nitrogen 13. We have some other models, for example, for a glucose analog that allows us to look at inflammation, regional inflammation. But there's just not enough time to talk about everything here, which requires completely different models because there are active biological processes involved in the transport of the glucose rather than passive diffusion. With passive diffusion, I would expect that it becomes closer to the first principle, but with the active transport processes, you need different equations that can characterize these processes. So as the final point, I think I want to do, if you go into imaging, and I guess you will come in biomedical engineering, you decide to become involved in pulmonary imaging, you probably get in contact with CT images or maybe some other method of density images. The point I try to make there is a strong argument that we think assumptions that the differences in density, for example, caused by gravity, if a subject is in supine position or prone position, is caused by changes in alveolar size. However, the CT does not allow us to distinguish between the blood volume and the tissue. And the blood volume at the alveolar level is substantial. So here is an old study, 87, an excellent study from the Hammersmith in UK, hospital in London, UK, where they had labeled carbon monoxide, so using carbon 15. And with the labeling of the carbon monoxide, the red blood cells get labeled, and the red blood cells are inside the vessel lumen, in contrast to the tissue that is outside. So that allows them to separate the blood volume from the tissue volume. So the blood volume from the total, and therefore they get the extravascular tissue volume. And it turns out that the extravascular tissue volume, so at the left bottom here, is relatively flat in contrast to the lung density that is on the top left, where you see there's a substantial vertical gradient. And I think we need to follow up on that. There is a high probability that the vertical gradient in the inflation of the alveoli, which we refer to often, may be partially associated with differences in blood volume in the vessels and the capillaries. So to summarize it, I think biomedical engineering is highly relevant for respiratory research as a highly interdisciplinary field. So I encourage you to look into it if you are interested. For me, I never wanted to change once I got in. There were so many possibilities, so many exciting things. There's a rich history to build on, well established. But there are so many unknowns once you go into a detail that are still important. For example, if patients get ventilated in the intensive care unit, and we still don't know exactly which settings of a mechanical ventilator could further reduce mortality in these patients. I think we have gotten better over time, but nobody is satisfied yet. There are still too many subjects dying, patients dying, and we think we can do better if we understand more details of the mechanisms. So for pulmonary imaging, I think the PET-CT, particularly from my perspective, my experience, combines the functional assessment using the high sensitivity of isotope concentration. So PET, so to make a comparison, so while CT with a higher spatial resolution gives me structural information. So to explain that with different words, I would say, if I need to find a radioactive needle in a haystack and I have a PET image, I know that there is a needle, or roughly where the needle is, because it has a very high sensitivity for the isotope. There's an isotope there that's decaying, and I can see it. I cannot say exactly where it is in a very accurate location, but I can say that there is a needle or how many needles there are. In contrast, with CT, I would have to see the needle to recognize it and say, oh, here's one, or here are 2 or 3. So that's the difference between PET with the high sensitivity for the activity, isotopes in very low concentrations, which is actually much better than MRI. The MRI is catching up with tracers, but PET seems to have a much higher sensitivity that we can, the concentrations of tracer we need much more cheaper with PET compared to MRI. And modeling, I think you may have seen it in my talk. At least I try to frame it this way, that modeling is basically essential for the quantitative data analysis and for the quantitative relationship. So quantitative relationship, for example, the asthma model of bronchoconstriction and bronchial tree. So I like to thank many people. So it's a short list. The actual list is much longer of people who we have collaborated with. I have collaborated with in our lab, Pulmonary Imaging and Bioengineering lab at Mass General. You can go to our website to see a few more details where all people are listed. I have included here people who were included in the work I have presented, particularly Jose Venegas, the senior principal investigator, Marcos Vitamello, one of the principal investigators, Scott Harris, and Guido Musch. Professor Gabriel, when he was in Boston, was participating in this and made groundbreaking contributions, and many others that I want to thank. And I want to thank you for your interest.
Thank you, Professor Tilo, for on behalf of our program, biomedical engineering program. Thank you very much for your clear, very illustrated, and very stimulating presentation on the subject. I'll invite you and the audience for a brief discussion, very brief discussion. We have some questions here. I have some more. And meanwhile, we'll be getting more questions and comments from the audience. So you mentioned, I'll try to summarize some of the questions because I think they mean something, they are somewhat similar. They have to do with lung mechanics, and that's my question too. And I'd like your comments on the subject. So the first comment is, the first question is, what's your view with respect to having a more detailed, a more fine-grained description of lung mechanics, including non-linearities in compliance and resistance and so on? Is it still important? Do you think so? Because this links to the other questions that were made here, and my question too, which is how to extract information using modeling, mathematical modeling, from the many and diverse imaging modalities that you have, because we know that, for instance, CT. The density information has something to do, but it's not directly linked to strain, to distension of the tissue, for instance. It has to do with aeration, and indirectly has to do with strain too. But and PET is a promise, and functional MRI too carry promises on bringing information about this particular question, which is very important, very dear to me and the group and Gabriel and so on, and Professor Janella also, who is the leader of the lab and has been working with that for a long time. So the first part of the question is it important to have this fine-grained information, high-resolution information on lung mechanics? And the second part is how to get that from the minimal. I know you like fine-grained information. I told the story at the beginning of this. So anyway, I'd like to hear your.
So I hope you're then not, if you have that expectation, I'm not sure you may be disappointed with my answer. So
Okay. Go ahead.
I think the point should be, I guess we agree on it, if we so what I tried to emphasize at the beginning was the relationship between reality and model, that the model and also the parameter estimation has a certain purpose. Yeah. And can we demonstrate that what we are doing has is meaningful for, I don't know, understanding a certain disease process, right? For example, the bronchoconstriction, the bronchoconstriction in area 3 that is relevant for asthma, I don't think it's this detail and this feedback mechanism is relevant for an ICU patient. Yeah, and it's abstract anyway, so it's not specific for a patient, right? But it captures the essence of the mechanism behind it. So with the nonlinearity, there is a double-edged sword in a sense, because some of the nonlinearity may also come from, so for example, if you were to use a single compartment nonlinear model and compare it with a two-compartment linear model, maybe the two can describe somewhat similar behaviors. Right, now which one is true? Right, maybe one or the other would help us to understand the disease process. Maybe imaging would be evidence for that it is regional heterogeneity rather than global nonlinearity. Right, so you subscribe to one, and that actually, now that you say it, it reminds me of the question, the debate in the field with small versus large airways. There are certain measurements, so with the force oscillation technique to measure ventilation mechanics. And there are arguments between two groups basically about the heterogeneity, right? And if that means small airways or large airways. And it is certain assumptions. They cannot actually resolve it. I mean, there is no way, as I tried to demonstrate, to with the structure of the model from the transfer function that we can derive to come to a clear understanding, in my perspective, if that is central or peripheral. You can subscribe to, there are two alternative models used in this field. One subscribes it to some airway heterogeneity, and the other one more to tissue heterogeneity, right? But neither one might be true, and you have to choose one because you cannot have both mechanisms and then determine which one is relevant. So that's the limitation I see in giving the answer, right? So I'm rather outlining the problem and giving you an answer, but I think that's what it is. And I wish we could get a better way, maybe by exploring more the imaging. And if we would see that there are regional differences in terms of the expansion is linear or nonlinear, maybe that could hint at certain processes. Right? I mean, if we see that the expansion is regionally heterogeneous, then maybe a global nonlinear model may not be a perfect fit. It may work, but may not capture that process. But on the other hand, clinically, it can still be relevant if it works, right? I mean, there are a couple of models that work clinically, although they contradict to some degree the physiology.
Okay, well, thank you. There are some questions here that have to do with that. There's a question about the use of ultrasound technology to get strain information of the lungs. There's a question. What do you think about using an array of? There are some other modalities you didn't speak about in your presentation, but we know that there is electrical impedance tomography and so on and so forth. Could you give a general overview of the relationship between the many modalities and information and getting information from the lungs?
So with ultrasound, my understanding is there are some attempts to improve it, but ultrasound suffers from the transmission in the lung, right? So you have a two-phase system. You have basically a sponge, so to speak, right, with open cells. And now you try to put an ultrasound signal in, but the ultrasound signal relies on reflections. So I think ultrasound is perfect for dense organs where you have certain interfaces with different densities so that you get the reflection of the signal. But with the lung having so many interfaces between the tissue and the air, there's a weak penetration, then you don't get a good signal back. There is one, but it's very empirical that they see certain lines in the lung, lines of reflection, and they are evidence for pleural effusion or so. But I would argue this works clinically and that is relevant, but it's sort of empirical and not quite that you get a detailed regional information about the lung. It's more evidence or indicator that may be sufficient or good, a robust indicator for clinical decision making, rather than telling me what the inflation of the lung is in that region.
Yeah. Just to make a point here, there is some attempts, and I think now it's a commercial device that uses sound, not ultrasound, to make lung images. So,
yeah, and there's this question from Professor Moria also. Thank you, Professor Moria, for the question. Do you think assessment of respiratory mechanics by force oscillation technique can help with image analysis? I think you mentioned that already, but please feel free to make any additional comment.
I think it would be interesting to have closer comparisons. And maybe to settle a few questions that come out of the assumptions that are made in the forced oscillation technique. Right, as I mentioned, so you have to typically there are two models used. One is sort of the more tissue-based, and the other one assumes. So once you assume that there's parallel heterogeneity, so two compartments with different time constants, you cannot then try to assess if there is a tissue component involved because of the limitations in the transfer function. So maybe imaging could help to guide certain interpretations, although we have done in the past, so in the early 2000s, some studies in parallel. Also, Jeff Maxim has done studies with MRI and force oscillation technique. And as far as I remember, he told me that he was surprised that in the he expected more of a change in the resistance during bronchoconstriction and asthma, but it was more a change in compliance that he got from the forced oscillation technique. And then he realized that this was somewhat matching with the imaging, because once the airway gets sufficiently narrow, there's no signal anymore coming from these ventilation defects. The contribution is in the single digits out to the flow, right? So how would you measure it? When we have much more noise in the flow and pressure measurements, then pick up single-digit differences from functional compartments.
Oh, thank you. I'd like to finish asking you What do you think the cutting edge in lung imaging and modeling is today? For instance, there's been a lot of discussion when I was there with Professor Marcus. We discussed a lot about how to use PET, some isotope, some biomarker, I don't know, to image strain, lung strain, and as far as I know, we could not come up with an answer, a direct answer. So, what do you think is the cutting edge is today in this field?
Yeah, it's always tricky. I mean, there's certain intuitions that you see on new developments that can be surprising. For example, uh, what goes a little bit in a different direction than you ask. In in asthma, for a long time, there was a very strong focus on airway smooth muscle, right? Because airway smooth muscle would narrow the airways. Now, a few years ago, a group published an excellent study showing that there are many mucus plugs in airways, and some persist for a long time. I suspect that the mucus plugs, again, may not be independent, but somewhat related to the narrowing, because if the airway is narrowing, then the mucus transport must be impaired, right? But I'm saying that as an example that the field was for a long time focused on one thing, and suddenly someone looked at something else that was a topic in the past, revisited it, and found that there is a relevant signal, right, that we cannot ignore. And maybe clinically it's very relevant or good evidence for the treatment that is needed. So with strain, I'm not sure if strain could be measured with an isotope, because strain is more the kind of expansion of the alveolus. The expansion itself, it can cause injury, but that's different. That's not the strain itself. Then you ask,
Maybe the stress.
yes. So the we would be interested in actually detecting the injury, and therefore we relate it to the uptake of the glucose, right, which is then related to inflammatory cells and the whole process. But it's not exactly. Even inflammation itself is poorly defined, right? It's a whole set of processes that can happen, right, involving different cells, etc.
Right.
But I think the strain analysis has gotten us pretty far in terms of seeing what is happening, right, and how strain is different in supine versus prone.
Okay. And Gabriel, do you have any comments you were mentioned? You have the right to comment.
Yeah. I would just follow in this question about cutting edge imaging. If it's that perfusion was always more difficult to image than anything that we are breathing, and now there is some new techniques like the dual energy X-rays. You think that perfusion will be more studied now than we had before?
Yeah.
Yeah, maybe. I mean, so there is a difference, so that I didn't go into. And I realized, to be honest, only recently. So what we are doing, our signal is strictly speaking capillary perfusion, because it is the tracer that is transported to the capillary and the diffusing in the alveolus. So the amount of activity in the alveoli is proportional to that capillary perfusion. It's only relevant once it reaches the alveolus. We do not see the activity at that point because it's gone from the other vessels. So we have a very focus on our technique, and we are limited to it to some degree, to capillary perfusion. With the dual energy, I think the dual energy I'm very interested in. It's promising because it seems clinically usable. Our method is complicated. It's more a research method, and in fact, I think we are the only one in the world who do it, use that method. Because of the constraints it has, technical constraints. So Yes, I'm very interested in it, but I have very much the focus on it. So when I'm interested in the method, what one of the first questions I'm asking is, what may be the limitations? What's the problem? Once I understand the problem, then I understand what I can use the method for. When I see only the promise, it can be anything. Maybe it works, maybe it doesn't. Once I understand the problem, then I see, yeah, that should work for that application or that, but it won't work for the other application. So that's why I start to ask early. So with the dual energy, it's strictly speaking, so by conceptually, it's a blood volume image. It's not a perfusion image. And I think for clinical purposes, that may be sufficient. Maybe for a lot of research studies, it's sufficient. But we have evidence that there's not a strict correlation between perfusion and blood volume. In fact, the relationship can change. So I think I am excited about the dual energy CT as the clinical avenue into regional perfusion. Although it is not strictly speaking perfusion, it's rather regional blood volume. But it can be robust, it can be unique, it's fast, in contrast to what we are doing, and it will be widely available. Right.
Thank you, Professor Thilo. I'd like to ask Professor Dilton Beck for...
Hi, Federico. It was a great webinar. Thank you, Professor Thilo. It's fantastic. I was following him in the back, and it was very good. Fantastic.
So on behalf of our team, of